All right, ladies and gentlemen, our next guest is a pretty smart human being. He's a professor in physical medicine and rehabilitation. He has a joint appointment in the Department of Physiology and Biomedical Engineering at the Mayo Clinic. He is the director of the Robert and Arlene Kogod Center on Aging. He is the co-director of the Paul Glenn Center for Biology and Aging Research. He is the scientific director for the Office of Translation to Practice at the Mayo Clinic. He is the chair of the NIH Cellular Mechanisms on Aging. His research team focuses on bench-to-bedside strategies, developed strategies to improve physical function, metabolism, and so forth in the face of aging and disease. And he is a highly awarded scientist with awards. He has received the Glenn Award for Research, the Nathan Schock Award, the Vicente Christie Award for Rising Star Award for Aging Research, among others. Plainly put, this is one of the most recognized and highly decorated humans in the field of aging, health, and longevity. But don't take my word for it. You can hear what he has to say. Please welcome to the stage, Dr. Nathan LeBrasseur.
Thank you. Appreciate it. All right. Well, good morning, everybody. It's great to be here and thrilled that we have such a good audience at this stage in the conference. We're going into day 2, so it's a reflection of your dedication and your endurance and your bravery. So I am a nuts and bolts scientist. I'm a traditional academic researcher. So for you to kind of tough it out and be here, I give you credit for that. And would like to thank the Vibrant community for the invitation and also their hospitality. It's been a great visit thus far. So I'm going to take you on a little bit of a journey today. I'm going to start to tell you about why I'm so passionate about aging, okay? What kind of inspires me to do what I do at a remarkable institution in the Midwest, Mayo Clinic. I'm then going to kind of take you on a deep dive, maybe back to the classroom in a way of understanding a very fundamental mechanism of aging that we think offers great opportunity. I'm not going to give you advice today on what you should be taking or what you should be prescribing to promote longevity in your clients, but I'm going to inform you about the process that we go through in a typical academic medical research center to understand a process that we think, if it's modifiable, could have a profound impact on human health and wellness, okay? So just to start, we can't do everything under our one roof, so we partner with external parties to help advance our ideas from concept to implementation. So I do have some intellectual property, and Mayo Clinic has intellectual property that I'll be touching on a little bit as we go through today's talk. This has all been cleared and approved, so I want you to know that. And then I'm absolutely privileged to work at an institution that is not really a boutique shop by any means, right? We see more than 1 million persons per year at our clinic, which many of you may have heard of. Hopefully most of you have heard of Mayo Clinic, but you may not know where it is. So we are literally in the middle of farmland, USA, in southern Minnesota, about an hour south of Minneapolis. And it's really a remarkable story if you haven't heard it. Ken Burns just did a nice piece on Mayo Clinic talking about our history and how we developed where we are, but a tornado came through this region, and the Mayo brothers were asked by the sisters of Assisi Heights to develop a healthcare institution in that place to take care of the people. They would build the hospital if the physicians would stay. And so many advances in science and medicine have happened at Mayo Clinic. It stays there. And I was just commenting in the back that the reason we're there, I think, is because of the work ethic and the dedication of our people, the Minnesota nice people, to help build the things that we build. So really a remarkable institution, a huge team of scientists and clinicians that I get to partner with every day to advance our knowledge and move the science forward towards clinical application. I'll just comment that the logo of Mayo Clinic reflects 3 things. So it's the shield has 3 components. The middle one is the largest, that's our clinical practice. It's 10% larger than the other 2, which are education and research. And I'm really going to tell you really about our focus of our research institute, which is the Robert and Arlene Kogod Center on Aging. So we benefit every year from about $1 billion in gifts from thankful patients. And the Kogod family was incredibly generous in 2007 and gave Mayo Clinic a transformational gift that allowed us to really focus on aging through the development of a center and recruitment of individuals like myself to that institution to really make this a top research priority for Mayo Clinic. And our vision is incredibly clear and simple. And our idea is to discover, translate, and apply interventions that target fundamental aging processes to optimize human health span. So I may be different than many of you in this audience who are clinicians and practitioners in that longevity space, but I can tell you that we're on the same page where we realize and fully appreciate the importance of understanding this very fundamental concept of aging. So I want to start off, after those introductory comments, with a very blunt question. And this really gets you to start thinking, right? Why are you not dead yet? If this was 150 years ago, average life expectancy for the folks in this room would be about 40 odd years, right? And we think about all the innovations that we've experienced over the past century, to the way that we do banking, to the way that we listen to music, how we get our news and share our information. But we don't stop to think about the fact that innovations in science and medicine will allow most of us to live until we're 80, right? That's remarkable when you think about kind of early stage infant mortality 150 years ago, the absence of vaccines and antibiotics, safer working conditions, healthier drinking water. All of these things have advanced the length of time that most of us will live in a way that reflects on the plasticity of aging and what we hope to accomplish. But it also kind of is a flagged away that says this has been a remarkable success. The fact that we now get 2 lives instead of 1. It's just a little bit different way of thinking about aging in and of itself. But what the theme has really been here is that aging is also coupled with a remarkable challenge. The fact that there is something about aging that increases our vulnerability to the overwhelming majority of health conditions that we see in the clinical setting. The overwhelming majority of our resources in healthcare, our time, our money, our energy is dedicated to the conditions on the right-hand side of the screen here that uniquely don't impact us in our 20s, our 30s, or our 40s typically, but are conditions that emerge with advancing chronological age, right? It's really remarkable. It takes us about 60 years to get our first chronic condition. It then takes about 4 more years to get number 2, 1 year to get number 3, and 6 months to get number 4. This exponential curve of aging that we've heard about during this conference. So this concept of getting older and suffering from multimorbidity is more the norm than the exception. Most older adults that we see clinically or see in our research studies, 20 medications is not uncommon. Multiple chronic conditions is not uncommon. So I really want to emphasize the point that there is something about just getting older that makes us vulnerable to so many of these different conditions. And to drive that point home, I just want to go through a few simple facts, right? Let's stop and think about aging and cardiovascular disease in the traditional clinical practice. When I talk to my colleagues about what are you addressing to minimize the risk of cardiovascular disease in your patients, and appropriately, they talk about the effects of abusing tobacco, of not managing high blood pressure or high cholesterol, or not managing type 2 diabetes. These pose incredible risk for the likelihood that their patients are going to suffer from this disease process. But the fact is, if you compare those risk factors to just celebrating your 60th birthday, these numbers are statistically based on large epidemiological studies, that your risk for cardiovascular disease goes up 72-fold just by making it to 60. Congratulations. This is what you get. Now, this isn't funny math that just has to do with cardiovascular disease. I think we all appreciate that 90% of cancers occur in those over the age of 50, right? We know that cancer is a disease of aging. But the truth is, this is not a public health announcement that we should smoke, abuse alcohol, and not worry about our body weight because they pose a limited risk compared to aging. But it really makes the point, right, that these are recognized and powerful risk factors for diseases that we all struggle with as clinicians, as parents, grandparents, loved ones, that we witness in everyday life. But again, just getting older is really what drives the high rate of cancer. Now, I do want to make a comment. I meant to say this earlier, that I am talking about aging as it is, right? But we should also pause and recognize that there are conditions in which aging is accelerated in many individuals. So if you're a childhood cancer survivor and you've been exposed to genotoxic drugs and different therapies that accelerate your biological aging, you're experiencing these conditions I'm highlighting 20 or 30 years earlier than you should, right? If you have HIV and have experienced some of the retroviral therapies, you've also experienced many of these diseases at a much earlier age. And even individuals with mental illness, we now recognize are experiencing age-related conditions at much earlier in life than they typically would. So as much as I'm making this about aging, I want to recognize that there are many conditions that accelerate these processes in individuals. And finally, Alzheimer's disease, something that we all fear, that we all talk about. Certainly Rosa Parks was prone to Alzheimer's disease just because she is a woman. She was a woman and lived long enough to experience this awful condition. The data are a bit mixed, honestly, about whether being female versus male increases your risk for this condition. It's likely that women just tend to live longer, so if we all live long enough, we'll experience this. But certainly if you have less than a high school education, you're at markedly increased risk for Alzheimer's disease. Rosa Parks, went through a lot more than most of us would ever imagine to get her high school diploma and also achieved more than 40 honorary doctorates, so she didn't have that risk factor, but she did have 2 copies of the ApoE4 allele, which really quite dramatically increases the risk for Alzheimer's disease. But again, even in the absence of those risk factors, just getting older markedly increases your risk for Alzheimer's disease. So again, I'll say it again, that I'm a very simple-minded, nuts and bolts scientist, but to me, what these data scream out is, what is aging? What is happening under the hood that predisposes us to so many different chronic conditions that I think even with the absence of really having a deep understanding of the etiology of these different conditions, you would say, well, there's no way that the causes of Alzheimer's disease, the formation of these plaques and tangles in my brain, have anything to do with the underlying biology or the etiology of something like cardiovascular disease, which looks so different on paper in its manifestations of what I see under the microscope. They're very different disease processes. How could there be a common cause at the root of these conditions that are so very different? So we talk a lot and think a lot about what is aging, and thankfully it saves me a lot of time because we've heard a lot about different drivers of the aging process. And these are really, simply put, different forms of wear and tear that we experience with time. I would actually argue that aging is probably a biophysical problem, right? It's wear and tear that everything experiences as we go on, is entropy. And these are manifestations of that entropy. These are the effects of aging. Aging is 3 things. I should have said this earlier too. Aging is universal, right? So not only is everyone in this room going to age, your dogs will age, your plants will age, your car will age, your toaster will age, your espresso machine will age. That reflects the entropy and the universality of aging. Aging is also progressive, so I don't want people to think that aging is something that we worry about when we turn 65 or 70. But aging is something that, we should probably choose our parents wisely, right? They pass on elements to us that will influence our aging, and whether it's 7% or 20% determined by genetics, it's really from conception to death that we think about aging, the aging process. And again, different life exposures can dramatically affect the trajectory of aging. It may take 60 years to witness the manifestations of aging as a dysfunction or a disease, but I can promise you that biology of aging is hard at work from day one, okay? So aging is also intrinsic. It's universal, it's progressive, and it's intrinsic. I can bury you in the safest chamber and expose you to the safest things and protect you from all forms of different external stimuli and stressors. But guess what? You're still going to age. And it's really understanding that intrinsic process of aging that gets us excited about, is there something that we can do about it? So we focus on these different hallmarks of aging, and I've shortlisted them here just to make the slide look interpretable. But again, it's understanding aging itself as a driver of so many of these different conditions that we talk about and think about, and I apologize if I don't have a circle for the conditions that you're most interested in. But we're at a new point now where we're having a very different discussion. We continue to have this important need to better understand the biology of aging. We're at the tip of the iceberg. We're still understanding the different wiring and mechanisms that drive this process. But this is no longer science fiction to talk about intervening on aging itself, but it's the science of today, it's the science of now. And that's reflected, I think, by the massive investments that people are making into this space. So you heard of Altos mentioned yesterday. This is an effort by Jeff Bezos to cheat death, putting several $billion into a company based in San Diego with another headquarters in London. They've stolen, I'm a little bit upset about it, some of the best minds in my field to go into those workplaces to help advance our understanding of the science of aging, but I can't blame them. It's 7-figure incomes for scientists, which is pretty unheard of. Google or Alphabet started California Life Sciences Company several years ago with a several $billion investment to build a team to better understand the biology of aging. We have an X Prize now for extending health span. I'm not sure how many of you have heard about this, but this was just launched. So there's an X Prize, a challenge, a $110 million challenge to reverse aging in older adults. And the goal is to change the age of the cardiovascular system, the musculoskeletal system, and the immune system. So there's an actual prize, a privately funded prize for the scientific community to figure out how to target aging. How many of you have heard of Hevolution? So Hevolution is very interesting. This launched about 3 years ago. Hevolution, like it or not, is health evolution. So Saudi Arabia has made 2 royal decrees in the past century, and Hevolution is one of them. And Hevolution is about targeting and understanding aging and improving aging for all of mankind. Saudi Arabia is putting $1 billion a year into aging research, new startups, and educational efforts. And I say this with caution because I think many of us have concerns about human rights violations from Saudi Arabia, but this is not investing in a new golf league or an F1 racing team or a soccer team, but this is investing to better understand aging and to do something about it. So we have to applaud them for that. $1 billion a year. For those of you who don't know, the National Institute on Aging has an annual budget of about $350 million. So this is triple what our government is spending on aging research, all right? So it's really the science of today, and of course, we're in Silicon Valley here, and there's countless startups that are starting in this space. Venture capitalists are very interested in what's happening in the laboratory setting, but this is really the time. It's the science of now. It's no longer science fiction. And the big deal here is that we're looking at ways to target aging. We're not trying to make better insulin sensitizing drugs or drugs to lower your blood pressure or maybe to treat certain cancers, but we're looking at ways to target aging with the promise that we could delay all these conditions as a group. And if you want to think of a better way to fundamentally transform human health, I would love to hear it. But can you imagine if we had a way to delay these conditions as a group, extend the number of healthy, active, productive years in our lives, not limited by disease or disability? This is really exciting, and this is coined the geroscience hypothesis, the idea that targeting aging itself can have an impact on these conditions as a group. And really the beauty of this and the deliverable is, not just for us as individuals, but the socioeconomic and political impact of compressing morbidity into our very final days is incredibly exciting. So that's my sales pitch. I am going to take now a little bit of a shift in direction, and just bear with me. My wife will tell you I'm not that smart, so I'm going to use analogies to kind of explain to you this fascinating biological process of senescence that I really kind of couldn't be more excited about. So I'm going to use an apple as the analogy. So as we age and experiencing these different forms of stress to our cells in our body, so we've heard about DNA damage. This is the instruction manual in your cells that tell every cell in your body what to do. It's the blueprint. It gets modified through epigenetic modifications that say, hey, you should be a skin cell, you should be a kidney cell, you should be a liver cell, and these are the things that you should do. Those things get altered with aging through the different forms of wear and tear that I was just referencing. We have changes in our mitochondrial health and function. Mitochondria get damaged. They're producing reactive oxygen species. They're spitting out kind of this foreign bacteria into our cells that trigger inflammation. We experience different forms of stress. The garbage disposals in our cells no longer work properly. So we just heard about mitophagy, but autophagy is a global term for the recycling process, the garbage disposals to get active in our cells, to get rid of old proteins to allow the new proteins to work. These different forms of stress that our cells experience, we have three options, right? We can repair that damage. We can be so damaged that we commit suicide, and that's a process called apoptosis, and we go away. Or there's this kind of purgatory middle state called senescence. And senescent cells are very interesting because, number one, they're a highly conserved mechanism across evolution to protect against the growth and spread of cancers. And they do that by turning on cellular machinery that causes growth arrest. And these are called cyclin-dependent kinase inhibitors, P16 and P21. I'll come back to those a little bit. That's why I'm emphasizing them. I don't want to pretend that we have the time to go over the biology of senescence, but just keep that in mind. The rotten apple is a very good analogy for a senescent cell because these cells look incredibly different. If I take a biopsy of a tissue from your body, look under a microscope, I can see a senescent cell because they have many alterations. So they have these really large nuclei. We call that karyomegaly. I don't know why I just say large nuclei, but we get fancy. We have alterations in the chromatin structure, which has profound impact on the transcriptional profile of these cells and what they do and how they function. They stain positively for an enzyme called beta-galactosidase. This is a way that we can use to identify these cells. I'll come back to that a little bit. And interestingly, these cells are damaged, but they don't die. That's given them this term of zombie cells that if you have never heard of senescence, just type zombie cells into Google and you'll learn all about it. But they've turned on programs that prevent them from dying. And these are called SCAPs, for senescent cell anti-apoptosis pathways. But think of them as turning on pro-survival pathways in a cell. These cells are also incredibly metabolically active, and that sounds like a good thing, but it's not. Their increased metabolic activity really drives the SASP, the senescence-associated secretory phenotype. This is really important. It's going to be a major theme in my talk because we talk a lot about inflammation and aging. We don't often talk about what the source of that inflammation is. Where is it coming from? And I will argue that senescent cells are a primary source of cytokines and chemokines that we detect in the circulation of older adults, right? They're not infected, but they have this smoldering fire that we know is causal for many conditions that we are concerned about. And the SASP, I'm very simple-minded, so we really focus on protein components, so cytokines, chemokines, matrix remodeling proteins, growth factors, but we're also learning a lot more about metabolites, microRNA, and other things that these cells transmit that may be communicating to distal tissues. And there's a really important point I want to make here, that there is something fundamental about aging, that these cells start to accumulate with aging across all organ systems that we've looked at. They're particularly enriched in organs affected by disease. And all of us in this room are experiencing senescence because you're having these different stimuli on the left-hand side of the screen that is telling your cell that it's damaged. So it will undergo senescence. But our immune systems are incredibly good at removing those cells when we're younger. But as we age, there is some dysfunction between the senescent cell and how it communicates with the immune system. There's still a lot of hand-waving in this space to understand this process, but they then start to accumulate as we get older. I've already mentioned they're enriched in tissues affected by disease, and we're still learning about why is senescence so important for health, right? So it's interesting, during development, tissues stop growing in part because cells will senesce and stop proliferating. When you deliver a baby, so during parturition, the uterus undergoes senescence to allow the child to be born. We know a lot about senescence in the context of wound healing, where some important factors can be secreted that promote that. So as much as I'm going to emphasize senescence is a bad actor, I want you to appreciate that it plays important roles in health as well. So this is a little bit of a detailed slide, and I apologize for that, but I just want to convey to you how one biological process we think could be responsible for so many bad outcomes. So first, when we think about aging and tissue regeneration, there is something very different between if I cut the skin of a 6-year-old or a 60-year-old, right, in terms of the healing process. Or think of that as an internal organ injury of how well a young system can repair and heal. We know that senescent cells, because they can no longer divide, are not able to contribute to the stem cell pool to repair a tissue. But perhaps more important than that, because of the factors that they're secreting, they are not allowing the stem cells that are there and healthy to function properly. So in Minnesota, we think of this as the seed and soil analogy, where you have this rotten seed, this senescent cell, but what's really bad is the soil, the toxic environment that these cells are creating because they are there. And I haven't said this yet, but we think senescent cells are maybe less than a fraction of a percent within a tissue. These are very few and far between, but it's the power of this SASP that is really affecting the health of the tissues and even distal tissues. In fact, we think a lot about paracrine senescence, that it's almost like, your neighbors are perfectly healthy, but then you walk into the show with the senescence phenotype and you're impairing their health and function. And in fact, we can put senescent cells into a young organism and cause some dysfunction. If we put those same number of cells into an old organism, we really cause problems throughout the system, just showing the power of the SASP on affecting the health of distal tissues. And I've talked a lot about kind of alterations in tissue health and structure and function, and we think about aberrant tissue architecture. So think about kidney fibrosis, liver fibrosis, arthritis. We can see how the factors that these cells are producing can really drive aberrant tissue architecture and impair tissue function. And again, a lot of talk in the aging space about inflammation, but not enough talk about what's the source of that inflammation. We now know that senescent cells not only robustly produce these factors associated with inflammation, but they also recruit, anchor, and amplify signals from professional immune cells throughout the organism to really create this very toxic milieu or environment. And lastly, just a brief mention, I really, 60% of my lab really focus on skeletal muscle aging. It's largely a post-mitotic tissue, so what does senescence have to do with cells that shouldn't be dividing anyways? But we now know that neurons and cardiac myocytes and muscle fibers, which are multinucleated, post-mitotic, fully differentiated cells, undergo this process as well, and that's very interesting. I want to just kind of stay on this theme a little bit. I'm probably doing too much, and maybe this is a slide that only Hari would appreciate, but he's probably giving a lab tour, so might be disconnected. But this is just giving you a flavor of kind of the nerdy stuff we do in the lab under the hood, where we look at different types of cells. So here you have a mixture of cells that we'd scrape from your arteries and endothelial cell, preadipocytes from your fat tissue that are typically known to differentiate and become the fat cells, the adipocytes that hold lipids within visceral and subcutaneous fat sources. Looking at fibroblasts, which could be in really any tissue in your body, epithelial cells, these are renal epithelial cells that are incredibly important for kidney health and function, or we look at muscle precursor cells or myoblasts. And C just means a control condition. SNC is a senescent cell, and this is looking at their secretory phenotype, or what they're spitting out into the media within a dish, right? And the only point I want to make here, and this is way over the top, is the fact that these cells are producing 100-folds more of these factors than a healthy cell. And that's really important. And we've been leveraging this information on these cells to help develop biomarkers to say, you have a high senescent cell burden in your kidneys, you have a high senescent cell burden in your heart, you have it in your liver, you have it in your lungs. We're not quite there yet, but we're getting there because we're understanding what are the unique signatures coming from senescent cells. And I'll come back to this at the end of my talk about why this is so important to advance our concepts to clinical application. But let me give you a couple of quick examples that we published recently. So this is just a infographic that is fairly informative. But when we collect those different secreted factors from what we measure in a dish, and then go into 2,000 older adults who we have access to in the clinical setting, not only can we use those signatures of senescent cells and what they're secreting and what's available in the circulation to predict the chronological age of an individual. Well, that's great. I could have asked you your birthday and figured that out. But more importantly, we can associate those different biomarkers of senescence with age-related diseases, dysfunction. So we've looked at physical function, loss of physical function with advancing age, loss of pulmonary function with advancing age. We can predict those events very well with this signature. And more importantly, when it comes to clinical decision-making, we can identify the older adults who are scheduled to have an invasive procedure and will have complications as a result of that procedure. We'll have a longer length of stay because of that procedure, or will be rehospitalized after that procedure. So very powerful tools to better understand this concept of biological age. If I put 100 individuals over the age of 70 in the room and say who should have surgery and who should not have surgery, the eyeball test is pretty good for about 5% of the individuals who should not have surgery because they look frail, and we can talk about that. It's a whole different discussion. But how do we know and identify individuals in the middle who maybe would benefit from prehabilitation or more robust transitional care planning down the road? So we're really excited about working on this biomarker component and have been doing a lot of work in that space. I'll just show one example from a recent publication from my group where we measured these levels of different biomarkers of senescence in 2,000 individuals. And we cherry-picked these individuals on purpose because you could argue that if they had diseases, that those disease processes could be driving senescence, which could increase the biomarkers. But we were really interested in the fact that if you're really healthy, right, you have no medical conditions at 65 years of age, you only have hypertension or maybe hypercholesterolemia, we're going to recruit you to this study, And we're going to take 2,000 folks between 65 and 85 years of age, and there's 4 kind of 5-year brackets in there, so we had about 500 individuals in each of those 5-year brackets. We measured these biomarkers of senescence, and then we had about a 10-year follow-up period on these individuals, and we said, can we predict who's going to die in that 10-year period? Now, of course, if we know your age, we're pretty good at predicting the likelihood that you're going to die, right? So if you're 85 instead of 65, the likelihood of you dying in that next window is pretty high. And if you're a guy, I'm sorry, your likelihood of dying is much more likely than if you're a woman. And interestingly, when we're looking at the hazard ratios on the right-hand side of the screen, that panel A, you can see age and sex shine as risk factors for dying in the next decade. And race plays a role in that too. And interestingly, if you have a disease, you're actually a little bit better off, and maybe you're getting more healthcare attention. But what's interesting to us is if we add our biomarkers of senescence to that, we can increase our likelihood of predicting whether you're going to die or not from about 70% to 82%. And that's pretty good, right? Flipping a coin would be 50%. If I know you're 85 instead of 65, I move up to 70%. But if we measure these biomarkers of aging, that's pretty impressive to us. So just showing some of the utility of these markers. Now, what you're probably most interested in, okay, I'm convinced this is bad. Senescent cells are causing damage and harm. Can we intervene? Is there something that we can do about this? So I struggle with this. I've been kind of giving a talk on senescence for several years. We made our first big discovery in 2011, and I've been struggling with kind of upping my game and coming up with a new analogy. So forgive me if I offend anyone. We often think about removing that rotten apple that spoils the cart as the best way to go after senescent cells. The media has had a field day with the concept of zombie cells. I don't know why it's so popular. I felt really stupid because I don't really get it. Like I don't get this whole zombie thing. How do zombies spread? And it's like, oh, they bite or whatever. Like I don't get it. So, but that's gotten so much press and attention. It's obnoxious. So we were on the Today Show not too long ago talking about this, and I just love this idea of the zombie stuff. But you know, the Washington Post has kind of picked up on some of our work and talked about zombie cells may hold clues to improving old age. The Associated Press, which then everyone else licenses in, is zombie cells central to quest for active vital old age. You know, Popular Mechanics, which actually, I didn't know this, but Popular Mechanics has been doing an outstanding job at following the aging field. They just had an hour special where they interviewed 5 of us about the process of aging and what we can do about it. Some pretty out there things about can we digitize memories and have you kind of go on for eternity in a robot form. I was like, what? This is nuts. But anyways, they are doing a good job at this. But I've also kind of grabbed onto this concept of zombie cells, and Nature, which is kind of the premier research publication for all scientists, have also kind of captured this zombie cell concept and really kind of opened the door and the floodgates to more people thinking about, well, what can we do about these toxic cells? And I just want to emphasize that, yes, we're thinking about small molecule approaches, biologics, and cell-based therapies, which I'll comment on here in a little bit, and even gene therapies. So this picture may look like someone you recognize. I don't mean to offend anybody. But I do think the bad or the negative social influencers is a really good analogy to think about senescent cells. And we think about ways to go after those senescent cells or the bad social influencers. There are a couple of options, and this is lingo that I'd just like you to know, because as we move forward, this is really the lingo that's been adopted by our field, and that's the concept of xenotherapeutics, so drugs that target senescent cells. And there are really 2 categories, and the reason that I like this social influencer idea is that we have Senolytics, so lytic to lyse to kill, which disable the pro-survival factors within those cells, okay? And that's really the equivalent of deleting the account, right? You can't tweet, you can't snap, you can't post, whatever, right? The latest and greatest. So those are drugs that we went with first because we've been using a drug repurposing strategy. So we can look in the literature, we can look at this incredible social network within a senescent cell that tells it to stay alive, what it turns on to stay alive, and then use small molecules to inhibit those pathways within that cell to cause them to self-destruct or commit apoptosis, okay? And I'm gonna give you a few examples of that. In parentheses, I put D and Q. This has been a combination that was first discovered, republished in 2015, of dasatinib, which is a common chemotherapeutic used for leukemia, and quercetin, which is a natural product you heard about the other day, enriched in the peels of apples, and then also navitoclax, which is a very specific drug which is a BCL family member inhibitor for those of you in that space, that this is another drug that turns off this BCL family of proteins that really drives survival in a cell. So if we turn that off, these cells will self-destruct and commit apoptosis. And of course, we're very excited because a large challenge for our colleagues in the cancer space is targeting cancer cells with cell-based therapies. And this is incredibly awesome time for targeting cancer, right? That we can engineer T cells or NK cells to go out and look and find these cancerous cells based on the proteins they have on their membrane and deliver a cargo to cause them to die, right? The problem is if you have a solid tumor versus a blood-based tumor, it's really hard to get those T cells or the NK cells to get to the core of the tumor. You can't do that. What excites us is that senescent cells are largely kind of sprinkled throughout an organ. There's not a clump of them or a cluster of them or a ball of them. So we're thinking very aggressively about engineering T cells and NK cells to identify the unique protein signatures of senescent cells to target those. And this is really a promising area that I would keep an eye on. I'm not going to talk about it today, but another interesting area, we just published a paper on preventing cancer chemotherapy-related cachexia, so the loss of muscle mass and function with cancer therapies, where we just turned off the SASP, so we quiet down the signals coming from these senescent cells. So this is kind of the muting of the social media account, no tweets, no posts, et cetera. And these are called SASP inhibitors, so senescence-associated secretory phenotype drugs that turn that off and prevent the cells from spreading their badness throughout an organ or a tissue or communicating to distal tissues. So that's an important area. I'm not really going to talk about that or show examples of that today. But I do want to walk you through a number of kind of what I think are pretty cool preclinical studies. So just so you know, kind of a little bit about how I run. I'm very fortunate. I direct this Center on Aging. We have 6 programs, 4 cross-cutting themes, a couple hundred people involved, based in Rochester, Minnesota. But we also have a site in Jacksonville, Florida, and Scottsdale, Arizona, where we're really dedicated in discovery science, translational research, and clinical application to understand aging. We also have a large AI component and bioinformatics component built in. But really, in my laboratory, about 15% of my folks work on cell-based models of aging and disease. So you saw kind of that one picture of cells in a dish. About 60% of our work is in animal models of aging and disease. And this is really a place that we can better understand the aging process and how interventions impact clinically important outcomes. So it's really, for those of you who maybe have mixed feelings on preclinical models and animal studies, this is really what informs us about how drugs are infecting a system, good and bad. And it also informs the design of clinical trials as we move down the road. So I want to walk you through some of that. So mice are not humans on many levels, but at 20 months of age, mice are about 70 years age equivalent of humans, okay? So when we look at aging mice and think about interventions to target aging outcomes, if we start with an intervention at 20 months of age and go to 24 months of age, think of that as kind of treating a 70-year-old till they're about 80 years of age. And what's really cool about treating with senolytic drugs is that we don't need them on board all the time to control something like blood pressure, but we call it a hit and run approach, where we can come in with a drug, zap your senescent cells, and then walk away and let time occur for them to reaccumulate, and we have to hit them again. We think we have to reduce their burden by about 30% to have a major clinical benefit. So that's kind of what we're achieving with this intermittent dosing strategy. That's really important because when it comes to human studies down the road, I just want to showcase how that could work as well. So this is just kind of the molecular details. If we intervene in an aged mice, we can show that the biomarkers of senescence are being reduced by the intervention. This is that chemotherapeutic drug dasatinib plus the natural product quercetin. But what's probably most impressive to you is that if we look at a cross-section of the thigh of the mouse, you can see that the older mouse treated with the vehicle has thinning of the cortical bone on the outside of that rim of the bone structure. But the trabecular bone, the spider web of bone that's really important for its structure and its integrity, is largely wasted away. But when we provide dasatinib and quercetin for just 4 months, so again, a relatively short-term intervention once per month, it didn't make a difference if we did once per week or twice per week, we markedly increased both cortical bone health and the trabecular bone health. So trabecular bone is kind of based on the number of trabeculi, their thickness, and the spacing between them, and those were all improved. And we look in the spine, we see similar changes, though cortical bone is not so important in spinal vertebrae. So just showing the impact there. So again, bone loss and aging sounds very different than if I talk to you about atherosclerosis. And atherosclerosis is a little bit tough. We have to use an animal model that does not have an LDL receptor. Mice don't typically get plaques in their arteries. But if we give those animals a Western diet, nothing too crazy, but just higher fat, higher saturated fat, and some cholesterol, and a little bit of sugar in their drinking water, they get marked plaque formation in their aortas. And you can see here on the left, and the coloring's not great on my slide, but you can see that that's the streaks that are occurring in the aorta of these mice. But if we treat them with this navitoclax drug, ABT263, which targets the BCL family members, we can markedly reduce the amount of staining in that aorta. We can reduce the number of plaques and the average size of each individual plaque. So this is pretty dramatic, right? In terms of targeting atherosclerosis with a similar approach that you would take for treating osteoporosis. Now, what about physical function? So for those of you like me who like, really kind of balance our aging and our fitness and our wellness on our physical function, here we're looking at mice treated in a similar period of time with this dasatinib and quercetin cocktail. If we do the Minnesota, or I talked to some Wisconsin folks last night, log rolling contest and see how fast they can run before they fall off the log. This is called a rotarod test to test neuromuscular coordination in a mouse. We see that improve with dasatinib and quercetin. We see their hanging endurance improve, which is just what you think it would be. And we see their exercise capacity on a treadmill to exhaustion is improved with this treatment. And interestingly, this was not a study about lifespan, but if we looked at animals from time of treatment to treatment cessation, starting at 24 months of age with this drug, about a 6.5% increase in lifespan, median lifespan improved by about 50 days, and maximal lifespan improved by about, again, 6%. So pretty remarkable effects with this, really I would call proof of concept intervention, and I'll come back to that at the end. Here's just a study, right? You want to study obesity in mice, what do? You treat them just like humans, give them a high-fat diet, give them Coke to drink. This is more of a fast food diet, and we see senescent cell burden increase based on the upper panel there of the molecular markers of this process. And we look at glucose tolerance. So just like we do in the clinic, instead of giving 75 grams of dextrose in a drink to a human, we give an injection of glucose to the mouse, and you can see how it clears that glucose. And we see improvements in the mice that are treated with the senolytic cocktail. This is really important, and this makes the point I made earlier. When we treat animals that have a form of Alzheimer's disease, we see that this is, again, the dasatinib and quercetin drug cocktail. We see a reduction in the number of neurofibrillary tangles in the brain. And this is really encouraging and important. We see a reduction in genes that are involved in this biological process of Alzheimer's disease. That's really important. If you can see the MRI images there, you see the white spots are the size of the ventricles, and they get expanded with Alzheimer's disease pathology. But when we treat with these drugs, we actually shrink the size of those ventricles. And I'd be very happy with that. That's a great outcome. But this slide also makes the point is that when we get rid of the bad actors, the toxic cells, the rotten apples, the social influencers, we now make that environment much more healthy for rejuvenation and regeneration. So now you can see that the proteins involved in neurogenesis, their abundance, that's a Western blot in panel F, that's just how much protein is there. You can visually see that the proteins involved in this regeneration are increasing, which is incredibly encouraging. And those are just some other measures of that process on the bottom of the slide. And then this was one of the earliest studies that my lab led looking at pulmonary function. So idiopathic pulmonary fibrosis is a very prototypical aging-related disease. Average age of onset is 66, and the really bummer news with that disease process is median survival is about 5 years. There are 2 FDA-approved drugs that do very little in terms of length of life, but they do improve pulmonary function for the period of time that the individual is alive. But we thought this was a very important place to play, so we kind of used an animal model of inducing lung fibrosis. We could see that lung fibrosis was associated with an increase in markers of senescence. And using 2 different kind of intervention approaches, I'll just have you focus on the D and Q because I've introduced that already, the dasatinib and quercetin. We could reduce the markers of senescence in the animal lung tissue. And then when we look at other markers of senescence, we see those reduced by the drug. And then PEN-H and compliance are basically looking at how resistant the lungs are to inflammation, to air, to expanding with breathing. And we can see both the fact that resistance to expansion is reduced and the compliance, the ability to expand, is increased in these animals. And we can see even outcomes like physical function, exercise capacity in the treadmill are markedly improved by removing these toxic cells. So I'll just end with this. I don't want to bore you to death with all the things that this can do, but I'm just trying to show you that, again, take senescence or take mTOR signaling or take the mitochondrial dysfunction or autophagy as your hallmark of aging. It's just to show you that a mechanism of aging can be involved in so many different conditions. It really is the promise of what we're talking about. And this was really a timely study where we can induce not COVID in mice, but a coronavirus infection. And by removing senescent cells in these animals, we can markedly improve the lifespan. So young mice do okay with the coronavirus infection. Older mice die within about 15 days. It's very predictable. You give them the virus and they pass away. But if we're able to get rid of the senescent cells, which we think are really important, and again, not only producing that cytokine storm that we talked about, but again, recruiting, anchoring, amplifying the signals from the professional immune cells, we can have a big impact on how individuals are responding to this infection with the use of Senolytics. And there are some clinical trials now underway to better understand and that process and the efficacy, potential efficacy of proof of concept Senolytics in that case. So I've really just tried to emphasize again the incredible power of, or potential, I should say, of xenotherapeutics. Still early stages. The drugs that I'm going to talk about, and I have been talking about, they're just in the proof of concept stage, not something I'd recommend that you rush out and try or prescribe off-label by any means. But this has been a big deal, right, to hit so many different conditions with a very similar intervention. And it's been getting a lot of press, and this is just kind of a nice summary statement that is free of the zombie or the social influencer reputation, but just the take-home message that cleansing the body of these toxic cells, we hope could postpone many of the diseases of aging, and that's really what we're focused on. And I'm fortunate to be at this institution that really prioritizes a union of forces for taking care of the needs of our patients, and more importantly, the unmet needs of our patients, and how we kind of come together as a group to solve very complex problems. And really our goal is to go from knowledge to delivery, and again, through this DTA approach of discover, translate, and apply. And I'll just mention that there's a lot happening in this space. So this is just a very simple and a bit dated slide actually now of clinical trials using interventions to target aging. Those in red are trials with Senolytics for conditions ranging from COVID, as I just mentioned, to frailty, to lung diseases, to osteoporosis, cholangiocarcinomas. These trials are actively underway, and we're really excited to see the readouts. I will say again that I'm asking everyone to temper their enthusiasm. We are not at a point yet where we have a laundry list of senolytic or xenomorphic drugs to choose from, but these are repurposed drugs that allow us a faster track to get into the clinical space just to see what's the safety and get a sense of if there's efficacy with these interventions. I thought I would take kind of the final stretch here to talk about a recently published clinical trial. What's really cool about this is I showed you the remarkable effects on bone in mice in 2017 that we published. And it's just really cool to think about the speed that we can move with repurposed drugs to go in 2024 and publish in the same journal, Nature Medicine, the human equivalent of that study. And this is a cool study, and it's the best designed study to date of Senolytics in humans, where we have a very well-controlled and structured study. There's a control group of about 30 individuals, an experimental group of 30 individuals. On the bottom of the slide is a little bit of a complex study schematic, but the point I want to make is that treatment is really just 5 doses during the 4-month intervention period. So intermittent treatment, not drugs every day, but again, the hit and run approach of knocking down those cells, walking away, and then coming back intermittently. Maybe one day you go in to get your teeth cleaned, to get your Senolytic, and do your taxes, and you're done, right? So that would be the big goal. And this main study outcome is nothing that's going to really impress you, but will show you that there was really no effects on the main outcome of bone health, which is bone resorption. And bone resorption is what most people look at because we don't really have approved drugs that have anabolic effects on bone. But interestingly, we had to choose a primary outcome for the study, and it was just kind of, let's pick bone resorption. And these are biomarkers of bone resorption. They're very good biomarkers of how bone is doing. If you want to see structural changes in bone, you have to go much longer. So for a short-term study, if you have a biomarker of outcome of interest, it's a much more practical readout. But we did see changes in bone formation over that time. And it's not a dramatic effect, but it really showed us that things are moving in the right direction. And what I want to do here is just kind of have a bit of a take-home message from this study. I welcome you to read it in Nature Medicine. But we also thought about, there's a lot of variability in the data, right? There's a big range of responses. So could it be that individuals who have different levels of what we think senescent cell burden could be based on biomarkers? So in this case, we use a measure in your circulating CD3 T cells, the P16 expression in those cells, as a rough marker of your systemic senescent cell burden. And there's good rationale for that. Other groups, not the Mayo group, developed this test and published it many years ago and showed that this correlates with chronological age. It goes up if you smoke, it goes down if you're physically active. So it's actually a decent measure of what we always say your systemic senescent cell burden. We don't know exactly in your bone, but we think it's just a rough measure. So if we divide these individuals into a top tertile, so these are the 20 individuals with the highest levels of what we think is senescent cell burden, and compare them to those in the lower levels, we actually see pretty promising effects both on bone resorption and bone formation in that third tertile. So on the top two graphs, you can see again those measures of resorption on the top, where we see a reduction in bone resorption, which you want to achieve with a bone building drug, as well as an increase in bone formation markers. And again, small study, just a proof of concept study looking at safety more than efficacy, but you can see that we're moving the needle in the right direction. So this is quite encouraging. And then surprisingly, again, a lot of noise in these data, and maybe the clinical meaningfulness of these changes could be questioned, but there's a statistical change that in tertile 3, we actually see a change in the radius bone mineral density. And again, not commenting on the magnitude of effect, but the fact in a relatively small cohort, we can see a meaningful change in those on drug versus those in the control group is encouraging. I share this study with you for another reason, and that's we think a lot about, well, how do we choose individuals for these studies? And it's interesting that those in the highest tertile of the senescent cell burden are all over the age of 70. So we've been talking this week about 100 is the new 30, and but 70 is maybe this very interesting break point. When we look at different biomarkers of aging, we see this kind of interesting hockey stick, to use a Minnesota analogy, that things are pretty steady through the 30s and the 40s, and we get into the 50s, we start to see this upslope. But certainly after the age of 65 or 70, we see a pretty big upswing in different biomarkers of aging, and that's been very interesting to us in thinking about the design of future studies. And the real big story here is that this is really the first randomized controlled trial of a senolytic treatment in healthy aging women. So we've done studies in disease conditions, but this was a perfectly healthy group. They did not have an indication for osteoporosis or poor bone health. We just took all comers. They had to be healthy. We did require them to have a certain level of that P16 expression in their CD3 cells to get into the study, but they were otherwise healthy. So when you think about, what's the future for your clinical setting focused on longevity and healthy aging, this could come into play, right? We're not there yet, but this could come into play. Again, the take-home message was it didn't reduce bone resorption, but it did have beneficial effects on bone formation. Really, the main benefits were observed in those with the highest senescent cell burden based on this one biomarker that we use routinely. But it really does set the stage for our efforts in the aging space as we develop new interventions, regardless of what hallmark of aging it's targeting, is who you choose to have in your study. And I'll just show you a slide on this in a second. But it also emphasizes our need that these are repurposed drugs. They were not designed to be senolytics or senomorphics. So as we work together with industry partners to develop better and more specific and more potent drugs, we'll see if a greater number of individuals with lower senescent cell burden would benefit from these drugs, and think of it more in a prevention space than just a treatment space. I've made a few comments about biomarkers, and I thought this would be just a relevant slide to this group as you think about your clinical practice, that yes, biomarkers play a large role in the science of medicine, but in clinical practice, even today, if we don't have an intervention to target senescent cells, biomarkers of aging and biomarkers of senescence could be used to choose the right treatment for the right patient at the right time, where maybe medical management is more appropriate than an aggressive and an invasive surgical management. And that's routinely done in many different types of cancer, where now even in organ transplant, we have a prehabilitation track for individuals who show evidence of advanced biological age based on either frailty phenotype or biomarkers of aging. And those could be prehabilitation strategies that leverage the foundation and fundamental aspects of healthy aging, right, of exercise, nutrition, sleep, et cetera. And for those of individuals who are at high risk for rehospitalization and surgical complications, those are the individuals that we need to strategize about how to best leverage the resources we have to ensure their effective recovery from a procedure. And of course, in clinical research, these same biomarkers help us identify individuals who should be included in the early phase clinical trials. It also gives us a signal about, does a new drug engage the target of interest, right? If I want to lower senescent cell burden, can I measure something in your blood? You probably don't want to give me a chunk of your heart, your brain, your kidney, or your muscle, though we do that quite a bit. but can I measure something in your blood that will tell me if this drug is doing what I want it to do and what it's intended to do? And then, of course, aging outcomes take time. And I'll comment to this on my last slide. It's tough for us and academics to always get the multi-million-dollar grant to do a 1 or a 2 year interventional study within a 5-year period, which is the typical grant window. So these biomarkers could serve as surrogate endpoints in those studies to say, I'm moving the biomarker, which means I'm changing the target of interest. I'm changing a predictor of a bad outcome down the road, whether it's rehospitalization, loss of physical function, loss of cognitive function. So biomarkers are really important. And I'll admit I didn't know what Vibrant was when I was invited to this conference, and I'm learning a lot about it, but this certainly is relevant to their interests and efforts. So I'm going to step back for just a second. I have a few more minutes left. And I have to say the talk this morning couldn't have been a better way to set the stage for this. This is just another way to think about the power of exercise and healthy aging. And as much as we're excited about genetic tricks and designer drugs, clearly the foundational components of healthy aging are the things that we've all been talking about and hearing about. And I couldn't be a bigger fan of those efforts. So this is just a great summary. And
Hi, Dr. Mike Evans, and welcome to this visual lecture I'm calling 23.5 hours. So I have a big interest in preventive medicine, which can mean a lot of things from, cancer screening to eating more fiber to having a good social network. And I mean that in the old sense of the word. Weighing less, drinking less, smoking less, controlling your blood pressure, cholesterol, and so on and so forth. So all these things are incredibly important, and I wouldn't want you to minimize your efforts in any one category. But I want to know what comes first. What has the biggest impact? What has the biggest return on investment? What makes the biggest difference to your health? So I did my research, and I found an answer, at least for me, and it's tricky because, all these things are sort of overlapping. But I picked out this intervention, and because of its breadth, it worked for so many different health problems, and that's what I found so cool about it. So just to kind of walk you through a quick list. So this intervention in patients with knee arthritis who receive 1 hour of treatment 3 times a week reduced their rates of pain and disability by 47%. In older patients, it reduced progression to dementia and Alzheimer's by around 50%. For patients at high risk of diabetes and coupled with other lifestyle interventions, it reduced progression to frank diabetes by 58%. Postmenopausal woman who had 4 hours a week of the treatment had a 41% reduction in the risk of hip fracture. It reduced anxiety by 48% in a big meta-analysis. Patients suffering from depression, 30% were relieved with low dose, and that bumped to 47% as we increased the dose. Following over 10,000 Harvard alumni for over 12 years, those that had the intervention had a 23% lower risk of death than those who didn't get the treatment. It's the number one treatment of fatigue. And of course, the kind of outcome of choice there, my favorite outcome is quality of life, which is really all of the above and really about making your life better. And this treatment has been shown over and over again to improve quality of life. So the question is, what's the medicine and what is 23.5 hours? So the medicine was exercise, mostly walking, so not triathlons. And let me just put it a different way. I think what I'm asking you to do is, if you think about your typical day, so there's 24 hours, and so you might spend most of your day, this varies obviously, but couch surfing, sitting at work, obviously sleeping. And what the evidence that I'm going to show you kind of tells me is the best thing you can do for your health is to spend half an hour being active, maybe an hour. And that if you can do that, you can realize all the benefits I've described in the previous slides. So let's just take it.
So a pretty powerful message, right? I mean, this is fantastic. This is from YouTube, nothing I created. I don't have the skills to do that, but really a powerful message and a nice follow-up to this morning's talk. And certainly physical activity comes in many different flavors of frequency, intensity, and duration. And there's a lot of thought behind that as well. And I'll just make the point that, the magical intervention was not a senolytic, but I would argue that the magical intervention of exercise does have senolytic and senomorphic properties. We published on this and kind of shared our thoughts on this in a few papers. And we've even done some trials now looking at the effects of exercise on the biomarkers of senescence that I've talked about. But clearly, we think senescence can be prevented through physical activity by preventing the triggers that drive this biological process. And in addition to that, there's without question a positive effect of exercise on the immune system to better identify those cells and remove those. And by doing that, we think exercise It's just one of the many effects that by reducing senescent cell burden is having an impact, such a powerful impact on such a large, broad swath of age-related conditions. And I'll just show you quickly, just looking at physical activity levels in about 1,300 older adults, we see marked reductions in those in the highest quartiles of physical activity in the biomarkers of senescence over a 2-year period. So everything from kind of inflammatory factors to matrix remodeling proteins to growth factors. This is a bit of a complicated chart, just comparing those in quartiles 2, 3, and 4 to those in quartiles 1, where we see reductions in those who are most active in these different biomarkers of senescence. And we have done kind of a controlled, structured exercise intervention in older adults over the age of 65 who are otherwise very healthy, and used that CD3 measure of senescence as a readout of interest. Surprise, surprise, 12 weeks of exercise improves grip strength, improves your ability to rise from a chair, to stand up, walk, and come back to a chair, reduces levels of fatigue, improves your sense of overall well-being, and improves your quality of life. What more do you need? But if you need more convincing, I can show you that when we look at the molecular signature of senescence in circulating CD3 cells, we see marked reductions in the signature of senescence. And what's most encouraging to me is that it's those individuals with the highest levels at baseline that appear to respond the best to this intervention. It can sometimes be hard to make healthy healthier, but here we're showing how exercise can reduce this high-risk predictor of bad outcomes in later life through its different mechanisms. So I'll just finish by stating we're pretty excited about xenotherapeutic drugs as a potential way to improve the health and function of multiple tissues. So far, this is in mice, not in humans, be careful. It's a very different approach, right? We're not talking about addressing the traditional clinical risk factors that we usually are taught about and talk about with our patients, but thinking about a different way to target aging itself. A lot of issues that we're addressing in the laboratory, from our technical understanding and ability to capture senescence in humans, still trying to understand whether there are beneficial roles that we need to be more thoughtful about. And then as we move into the clinical setting, this is an entire lecture on kind of what clinical paradigms will be most informative. A lot of discussion about really targeting conditions like idiopathic pulmonary fibrosis, where there is no known treatment or cure. This concept of the TAME trial of targeting aging with metformin is a new approach that the FDA is open to of, as I mentioned, 50 or 60 years to chronic disease 1. Can we delay the onset of chronic disease 2, which is typically in 4 years? So that's another clinical trial design that we're thinking about. Improving response to different interventions in older adults. So mTOR inhibitors have been used to look at treatment responses to vaccines and whether or not respiratory infections change in the next period of time after that vaccine. That's a very clever trial design to think about. And then, of course, thinking about improving resilience to physical challenge, such as surgical and medical interventions. So with that, thank you very much for toughing it out. I appreciate your attention. And here's a selfish plug. We also have a book on healthy aging. Imagine that. So this just came out in January. It's a very user-friendly guide, a little bit conservative, nothing too aggressive or cutting edge, but it's really sound evidence-based advice that you may want to share with your family members or loved ones. So thank you very much.